Okay, so we're gonna in this next section we're gonna be talking about equilibrium. And equilibrium is a special set of circumstances when the net force acting on something is equal to zero and the net torque on something is also equal to zero, which means that P, or momentum, is constant and L, also constant angular momentum. Now, what this means is that something is moving at a constant speed, whether it's at rest or whether it's traveling at a constant speed. But in all the examples that we're going to look at for equilibrium, they involve objects in rest, but all of this does apply to objects moving at a constant speed as well. And just because we don't have examples of those doesn't mean that they don't also fall under this set of circumstances. As we analyze circumstances for torque, we're going to be using net force equations and net torque equations. And really, there's three kinds of equations we can write. We can find the sum of the forces acting horizontally, the sum of the forces acting vertically, and the sum of the torques. Okay, so these are our three equations, and all of them will add up to be equal to zero because of the fact that a system is in equilibrium. Now remember, if it's not in equilibrium, this is MA, and this is I alpha. And that is still true of those situations where something is not in equilibrium. And I don't want you to forget that in the process of this chapter, because this chapter is focused only on the circumstances where this is equal to zero. There are plenty of other circumstances where these things are not equal to zero, and we don't set them equal to zero. Okay, but the key to this chapter is these three equations and being able to draw a free body diagram. Okay, so we're going to first look at a situation in which we have these beams with forces being acting on them. And so before we go into this question, I want you to look through these options and decide for which of these situations can the sum of the forces acting in the y direction be equal to zero and the sum of the torques be equal to zero. Okay, and as we answer this, what we're going to say is that these forces can be adjusted in strength. Okay, so I'll actually eliminate this piece. So for which cases could it be that the sum of the torques is equal to zero? Now the key to answering this is that since the sum of the torques is equal to zero, that there's a thing that we can do when the torque adds to be zero. We can move the point of rotation to wherever we want. Okay, because since it's in equilibrium, it's not going to change its rotation, which means that we can pick any point and our analysis is valid around any point because the net torque is zero. So go ahead and answer this real quick. Pick the options that could be in static equilibrium. Now let's go through them. Okay, so the idea here is if I can pick a point about which the forces drawn would cause this to rotate, then it can't be in equilibrium. So for example, if I draw a point right here, this system is going to start to rotate clockwise because each of these forces is pulling it clockwise. The same with this example here. If I draw a point right here, this system is going to rotate counterclockwise. Now you could imagine a scenario where you drew a point here where it wouldn't rotate, but all I have to do is find one point where I could show that it would. Okay, if I draw a point right here, this system is now going to rotate counterclockwise. For this one, there's no point that I can draw where you can't keep it in equilibrium based on these arrows, because if I put it here, I've got opposing torques. If I put it here, I've got opposing torques. Same if I put it here, or if I put it right here. Okay, so this system right here is in equilibrium, or could be potentially in equilibrium. The same with this one right here. Okay, this is in equilibrium. Same with this point, and this point. There's no way I could, in each of these circumstances, I could adjust these forces to keep this object in equilibrium. And finally, this one also in equilibrium. Okay, this torque is balanced out by that one. Right here, this torque is balanced out by that one, or I guess these three torques are balanced out by that one. And then we could draw it right here. These balance each other out, and those balance each other out. So for C, E, and F, it could be in static equilibrium. In A, B, and D, there's no way it could be in static equilibrium as long as those forces are not equal to 0. Okay, and so we actually have we're going to talk about a couple kinds of equilibrium. We have stable equilibrium, in which something is very difficult to move out of equilibrium. You can imagine like the table that you're sitting at school, like in our classroom, our lab tables. Or we have unstable equilibrium, something where it's really easy to tip over. So let's say you have like a glass of water. That would be in unstable equilibrium because it's easy to knock over a glass of water, where it's difficult to tip over the table. And we're going to talk about those differences, why. Tipping something has to do with one thing, okay? If I have this object right here, and let's say it's got a center of mass located right here. In order to tip this object, gravity pulling at the center of mass, in order to tip this object, I have to get this center of mass to be outside of the base. So as I push this object over, the center of mass kind of rotates up. I can get up to this point where it won't tip, and then if I push it past this point, now gravity is going to cause it to tip over. Because at that point, gravity exerts a torque on the center of mass, causing it to rotate. Okay? Between here and here, it's going to rotate back down to this stable position. Once it gets over to here, then it's going to rotate the other direction. Okay? And so things that are easy to tip, that are unstable, have very narrow bases relative to their center of mass. And things that are stable have the center of mass further down relative to their base. Okay, let me show you an example of that. So we have a couple objects here. This would be kind of like a book that's on its end, and this would be maybe like a block, like that kids play with or something. Okay, and so looking at this, you can clearly see that this book is much less stable than this block. Okay, and the reason why is what I just mentioned. The width of it is very small relative to the height of its center of mass, whereas this block is very wide relative to the height of its center of mass. Okay, and so this is really easy to tip, where this is really difficult. Now, I'm going to mention another concept here that's also an important factor. Okay, you have to think about energy as well, because when you're tipping something, you're actually lifting its center of mass up a little bit. It's going to, as I rotate this upwards, you can see that that center of mass, as I'm rotating it, gains height, which means that I'm giving the object potential energy. Okay, so when I tip this, I have to give it a little bit of energy, and once it passes that equilibrium point, it releases a lot of energy. Okay, so it's got kind of like a potential energy curve that looks, for this book, it would look something like this. Relative to horizontal position, you got this point where you have this little like valley, and that at the moment where it's here, it's kind of like right here in this valley, and then I give it a little bit of energy to push it out of the valley, and then all that energy is transformed into kinetic energy right away. Okay, and then for this one, it's in a much deeper valley, because in order to tip this, I have to get the center of mass all the way up, I mean, probably like to about here, which is a big change in height. And so for this one, we're going to have like a potential energy curve that looks more like this. And I have to put in a lot more energy to get it to tip. I have to raise it up a whole bunch more to get it to tip over. Okay, and if you've taken chemistry, I guess probably if you took AP chemistry, you might have seen graphs like this, because graphs like this are use similar graphs like this to look at chemical reactions and talk about activation energy to activate a chemical reaction. Okay, so but what makes this stable is that it requires much more energy to tip over than this one. This one requires a very tiny change in energy, so like maybe like a small gust of wind could knock it over, whereas this requires a significant increase in energy to be tipped over. The thing I glossed over in that last example is this distinction between center of gravity and center of mass. Okay, so when we're talking about tipping, the thing that's important isn't center of mass, it's the center of gravity, or the point that we say gravity acts on objects. And it's essentially the same thing. Okay, if this is the center of mass of a small object, that would also be the center of gravity, the place where gravity acts. Okay, and this is true for all all objects where the center of where G is the same for all parts of it. Okay, so if G here and G here are the same, that means that the center of mass and the center of gravity are also the same. Okay, but let's think of an object that's super, super big relative to the Earth. And so as you move further away from Earth's surface, G gets smaller. In a situation like that, the center of gravity is actually a little bit closer to the base than the center of mass, because of the fact that gravity is stronger near the base than it is near the top. Okay? We're not really going to talk about circumstances like that, but it's an important distinction between center of mass and center of gravity. Now, as we mentioned, if you're able to move this center of gravity outside the base, then the object becomes unstable and it will topple. Okay? And then let's say that we were suspending this object. If we were to somehow suspend it on an axis through that center of gravity, then it would be placed in equilibrium. It's going to just be because there's no torque caused by gravity, since the radius for torque to act would be equal to 0. Alright, and then one last thing. The last thing we're talking about here, if we take an apple and we skewer it with our thin rod, so here's an apple, we're going to stick a rod through it, okay, and allow it to freely rotate, it's eventually going to come to rest, and when it does, where will the center of gravity end up? So let's say we're skewering it somewhere near the top. Where will the center of gravity end up and why? The answer is right down here, because this is when it's in equilibrium. Okay, that center of gravity is at its lowest point, can't get any lower than that. You can imagine that anytime, if this is just like a cross section of it, anytime that center of gravity is not at equilibrium, it's pulling down at some angle relative to this radius, causing a torque. Okay, so if it's over there, it's pulling it down that way. If it's over here, it's going to cause it to rotate the other way. And then at the point where it's directly downward, it no longer causes a torque. So eventually, this is the place where it will end up.